All right, this is the second part of our lecture on October 29th, and we're going to start the second part with this question here. N, L, and ML for the orbitals of the 4D subshell. We know that N can take on the values of 1, 2, 3, so on and so forth. L can take on the values of 0, 1, 2, all the way up to N minus 1. ML can take on the values of negative L, all the way up to 0 to positive L, like that. So if we have a 4D, the 4 represents our N, the D represents our L. And what did we say? We said L, an orbital, when L is equal to 0, 1, 2, 3, we have an S or a P or a D or an F. And since it's a D, our L value must be 2. So far we've got our N is equal to 4 and our L is equal to 2. It's asking us to give the values of ML, and the only possible values are -2, -1, 0, +1, and +2. And that is the answer to the question. Those are the values of N, L, and ML for all of the orbitals in the 4D subshell. Remember, we said that when we have a D orbital, there are 5 types of orbitals, right? So S only has one orbital, one type of orbital. For P, there are 3 of them. For D, there are 5 of them, right? And for F, there are 7 of them. Well, let's think about it. If I have a total of 5 orbitals, right? Look, I have 1, 2, 3, 4, 5 ML values, because the ML represents or each ML value represents a type of d orbital. Okay, let's move on from there. This slide I probably should have put earlier on in the presentation, but we'll just kind of take a look at it quickly. Again, the magnetic quantum number, right? ML represents orientation in space. And so when I have a p orbital, there's 3 possible ways I can orient it. I can put it on the x-axis like this. I can have it on the y-axis, or I can have it on the z-axis. That makes sense because we have 1 ML value, 2 ML values, 3 ML values. What else? If we look at the d orbitals, what are the possible values when my L is equal to 2? That means that I have a d orbital. That means there's 5 orientations in space. Look, 1, 2, 3, 4, 5. And here are those d orbitals, and we talked about them earlier this evening. Nothing really new there. Well, with all that in mind, let's try another problem. This is question 7.9. It says, what's the total number of orbitals associated with the principal quantum number n is equal to 3? Well, when I have an n equal to 3, what are my possible values of L? My L can be 0, it can be 1, and it can be 2. It can't be 3, right? We can only go up as far as n minus 1. So let's think about that. If I have L is equal to 0, what are my possible values of ML? My ML can be a 0. If I have my L is equal to 1, what are my possible values of ML? -1, 0, and +1. If my L is equal to 2, what are my possible values of ML? -2, -1, 0, +1, and +2. Each one of these ML values represents an orbital, okay? Each ML value represents an orbital. Okay, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a total of 9 orbitals. Okay, so we get 1 s orbital, 3 p orbitals, and 5 d orbitals. 1 plus 3 plus 5 gives me a total of 9 orbitals. There we go. And that's the answer to the question. Now, for the energy levels of the orbitals that we've looked at so far in a single electron atom, when we have a principal quantum number, sorry, the energy depends on the principal quantum number only. But that's for a single electron atom. Now, how many single electron atoms do you think we're going to look at? I mean, not that many. Once we get into, we can only make so many cations, right? Before we run into some complexities there. So if you have a single electron atom, the orbital energy only depends on it. Now, again, we're going to look at very few cases, okay, where that would apply. What if you have a multi-electron atom? Well, it depends on two things. It depends on n, the principal quantum number, and it depends on L, the angular momentum quantum number. You can just scratch this part off here. That's a typo. I didn't mean to have that in there. Okay, you can see that we go from a 1s, right? As we increase in energy, we go from a 1s to a 2s to a 2p. Let me try to clean this up. To a 2p. And then what's next? We get to the 3s, right? I'm just following the axis here. Then we have a 3p. Okay. Then we mix up, right? It's not just depending on going from an n of 1 to 2 to 3, right? We see that we kind of swap them over here. We go from a 4s to a 3d, and then to a 4p, so on and so forth, right? So you can see that it doesn't follow the same order. And the reason why, if you're like, well, why would a 3d be higher in energy than a 4s? Well, that's due to something that's called orbital mixing, which is beyond the scope of our class. But I can show you a much easier way to get the energy of the orbitals in the correct order than to try to memorize this here. I can show you a much, much, much faster way. Let me show you. We back up all the way to here, where we started out. I'm going to erase some of what's on here, okay, just to kind of keep things organized. Look, you can see that if you follow this, and I'll erase all this stuff too, I guess. As we start adding electrons to any atom, pick any atom in the periodic table. I don't care what it is, copper. It's got 29 electrons. You're always going to start at the beginning. You're always going to start here. 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6, 7, 8, 9, 10, so on and so forth, okay? 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and then you'd be at copper like that. You always start at the beginning. And look what the order that we went in was. Let me erase all this and I'll show you. We went from the 1s, right? The little 1s. Then we went to a 2s. Then we went to a 2p. We went down to a 3s, up to a 3p. Then we went to a 4s. And then where did we go? We went from the 4s to the 3d. So as long as you remember that with the transition metals, when you start here, you don't have the principal quantum number of 4. You drop it down by 1. You're always going to have them in the correct order. Okay, so that's why I showed you this first. And if you're wondering, well, come on, Mr. Dion, that would mean for any atom in the periodic table that's got more electrons than copper, I'd always follow the same order. Is it always the same order every time? The answer is yes, absolutely. So if you do enough of these, you're going to start to have it kind of memorized. I wouldn't depend on that. You always have a periodic table with you on all of your exams, but you can use that to help you. All right. Well, let's look at a couple more rules, okay? As I told you at the very beginning of the lecture tonight, I said what you're going to be able to do by the end is you're going to be able to assign a principal quantum number for every electron in any atom on the periodic table. Even atoms that have a lot of electrons, radon, 86 electrons, you can be able to assign all of them. But where do we put those electrons? Well, as I showed you on the last slide, I started at the 1s, then I went to the 2s, then to the 2p, then to the 3s, then to the 3p. You're always going to start at the bottom and work your way up. And that is a rule or a principle, and it's got a name. It's called the Aufbau principle. Sometimes we call it the building up principle. Okay, you're always going to fill up electrons in the lowest energy orbitals first. Let me show you something else here. I take this 1s orbital. If I zoom in on that 1s orbital, my 1s, okay? Remember, an s only has one type of orbital. A p has 3 types of orbitals. A d has 5 types of orbitals, and F has 7, so you'd have 7 lines. How many electrons, and this is a question for you guys, how many electrons can be held in each orbital? Not a trick. I mentioned it a couple times this evening. How many electrons in each orbital? Maximum. 2. Exactly. Whoever answered 2 and 2 and 2, you're all 100% right. Every orbital can hold a maximum of 2 electrons. So that means that in the 1s orbital, I can put 2 electrons. Let me show you how I write those electrons. Okay? Since ms can be equal to plus a half and minus a half, and since no two electrons can have the same set of 4 quantum numbers, that means one of the electrons is going to be plus a half, and the other electron is going to be minus a half, but we don't write them like that. We write them as arrows. Okay? We draw one of them pointing up like that, and we draw one of them pointing down like this. Okay? So this would be 1s with 2 electrons, and I would actually call this a 1s2. And the superscript means 2 electrons. Okay, and we're going to see that more and more as we proceed. But the Aufbau principle means we start with lowest energy. That means you always start with a 1s. Then you go to a 2s. Then you go to a 2p. Then you go to a 3s. Then you go to a 3p. Then you go to a 4s. Then you go to a 3d, just like I showed you. Okay. The next rule is called Hund's rule. I call it the bus rule. Bus rule. Okay? Let's say you're, on a bus, or you're getting on a bus, a city bus, okay? And there's 1, 2, 3 seats. The first seat has a person in it, and the second seat has a person in it. Here's you. Okay, this is you. What are you going to do? Who can tell me which seat you would take? Would you take the first seat? Would you take seat 1, seat 2, or seat 3? What would a normal person do? Well, at least what I would call a normal person. Which seat would they go with? Exactly. Trevor, you think the same way as me. Personally, I think that if you were to be like, hum-de-dum-de-dum, I'll just go sit over here next to this person. That would make you insane, okay? Unless it's your friend, okay? If you were to say, oh, I'll just sit here next to this person's going to think you're a weirdo. What do you usually do when you get on a bus? If there's an empty seat, you take it, okay? That's what Hund's rule is. Now, phrased another way, it says the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. Now, what the heck does that mean? Well, instead of writing those seats, we'll write orbitals. We have 1 orbital, 2 orbitals, 3 orbitals. So imagine these are p orbitals. Imagine this is a px, a py, and a pz. Remember, I told you that an electron can have a positive spin or it can have a negative spin. Parallel spins mean the spins, arrows are pointing in the same direction. Okay, same direction like that. So if I had 3 electrons, I wouldn't put any 2 electrons in the same orbital. I'd fill them all like this, right? This is the greatest number of parallel spins, where they're all spinning in the same direction. Okay, so let's say you had 5 d orbitals. Okay, the d orbitals 1, 2, 3, 4, 5. If you had 4 electrons, you always start like this: 1, 2, 3, 4. If you had a 5th electron, you'd put it here. That's the greatest number of parallel spins possible, is 5. Only once you get each one of these orbitals, each one of these seats is half filled, then finally, if you were the next person, okay, what would you do? You'd be like, damn it, I'm going to sit next to somebody, okay? That's the only time you would go sit next to somebody. So once all the orbitals are half filled, that's when you can start putting more electrons in like that. Okay? So that's Hund's rule. For orbitals of filling in a multi-electron atom, that you can use this table right here. It's outlined in our book. I used to teach it in detail in this class, but I gave up. And the reason why I gave up on teaching the material, no, I gave up on teaching this. The reason why is because if you use the order that I showed you in the periodic table, it follows this exact order, going from a 1s to a 2s, to a 2p, to a 3s, to a 3p, to a 3d. Sorry, ugh, I'm not following the arrows here, am I? From a 1s to a 2s to a 2p, then to a 3s, 3p, 4s, right? You follow the arrows going down like that. Again, there's a reason why I don't teach it, because it's much easier to go by the periodic table. All I would say about this table is, if you find it easier to write this down every time and use it, by all means, go ahead. Okay, but again, I'll always provide you with a periodic table. Well, let's try another practice problem. It asks us to write four quantum numbers, write the four quantum numbers for an electron in a 3p orbital. What are the four quantum numbers? Okay, they are N, L, ML, and MS. Well, if we have a 3p orbital, what do we know already? We know that N is equal to 3, and we know that L is equal to 1. Okay, we get that much. So we could write this down. We could say 3 and then 1. Well, if L is equal to 1, what are my possible values of ML? ML could be -1, it could be 0, and it could be +1. Okay, so let's write those in. It could be -1, write it again, it could be 0, and it could be +1. Now, if you're wondering, like, why did you write all of them out, right, like that? Well, in fact, I'm going to copy that and paste it, and I'll show you why in a second. Let's copy this, copy, and I'm going to paste it over here. The reason why is because there's two possible values for MS, right? MS can be +0.5 and -0.5. So I could put +0.5 here, +0.5 here, +0.5 here. I could put -0.5 here, -0.5 here, and -0.5 here. There you go. Now, if you're like, well, come on, Mr. Dion, it's only asking for one example of the four quantum numbers for an electron in the 3p orbital. But remember that a p orbital, there's three types of p orbitals, px, py, pz. Each one of them can hold a maximum of 2 electrons, right? 1, 2, 3, 4, 5, 6 electrons total. Look at this. I have 6 sets of quantum numbers total, right? What did I tell you at the beginning of the class tonight? I said for every single electron in an atom, you're going to be able to come up with a unique set of quantum numbers. There is no set of quantum numbers in this yellow box that is identical to another one. They're all 6 of them different. And you can take an electron like, or sorry, you can take an atom like, you know, ytterbium, okay? 39 electrons. You can write a set of quantum numbers for all 39 electrons. All right, and if you're like, are you going to make me do that? Well, in the practice problems, yes. So make sure you go over them in gross and dirty detail. That brings us to the subject of electron configuration. An electron configuration represents how electrons are distributed among the various atomic orbitals in an atom. We always write electron configurations as so, where we have the number, a number first, which is the principal quantum number, right? N, okay? Then we have the angular momentum quantum number, but we write the letter. And you know that when L, an orbital, how many times have I written this out this evening? I don't know, 0, 1, 2, 3. We know we have S, P, D, or F. So that tells us that our L is equal to 0. And then this tells us the total number of electrons in the orbital or the subshell. Well, how many possible electrons can you put in an s orbital? There's only one type of s orbital, right? Because when L is equal to 0, the only possible value of ML is 0. One possibility. And you can have 2 electrons in it. Well, a hydrogen only has 1 electron. It's the first element in the periodic table. And so its electron configuration would be this, 1s1, like that. That's the electron configuration for a hydrogen. The orbital diagram, there's a couple of ways you can do it. You can either write these boxes like this. Mr. Dion is not a big fan of the box. The way that I do it is this. I just draw a line instead of a box, 1s1. And you can either write a double-headed arrow like that, that's acceptable, or probably if you look at my solutions, I just have a single-headed arrow. The single-headed arrow means the same thing as the double-headed arrow. It's just a faster way to draw. I can't take all that time to draw that extra side of the arrow, of the arrowhead, I guess. All right, so that's electron configuration. Let me check on something here quickly. Yeah, I just wanted to go over a couple things before we move on. Okay, let me just check something here quickly. Okay, let me get us a blank document here and talk about some more electron configuration. You're going to need a periodic table because it's hard for me to switch back and forth. Well, let's say we had helium. Okay, helium has 2 electrons. Okay, helium is found in the first period, so its principal quantum number is 1. It's in the s block, and it has a total of 2 electrons, so 1s2. That would be the electron configuration for helium. All atoms that have more than 2 electrons are always going to start with 1s2. If I have lithium, for example, lithium has a total of 3 electrons. I have 1s2. Then if I go back to my periodic table, here, lithium is found right here in the periodic table. It's got 3 electrons. I have 1, 2, 3. That means I've got 1s. Let me write my lithium. For my lithium, I've got 1s2, 2s1. What if I had, let's say, boron? Boron is found right here. For boron, I have 1, 2, 3, 4, 5 electrons, right? Boron has 5 electrons. So I have 1s2, 2s2, right? 1, 2. And then the 5th electron comes from 2p, 2p1, like that. What if I have nitrogen? Nitrogen has a total of 7 electrons. So it goes nitrogen, carbon, boron, carbon, and then nitrogen, right? So it's 1s2, 2s2, 2p, what? Who can help me out? Exactly, 2p3. Right, when you tally up all of these superscripts, how many total electrons were there in lithium? 3. Look, 1, 2, 2 plus 1 gives you 3. How many total electrons are there in boron? 5. 1, 2, 3, 4, 5. How many total electrons are there in nitrogen? 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the number of, if you tally up all the superscripts, they should equal the total number of electrons in the atom. Let's cover a couple more concepts here. Paramagnetism and diamagnetism. If you draw out the electron configuration and then draw the orbitals of the electrons and fill them in, if you have unpaired electrons in an orbital, if you have an unpaired electron like this is an unpaired electron, this is an unpaired electron. Okay, unpaired means there's only one in an orbital. Those kind of substances are going to be attracted by a magnet, and we call them paramagnetic. If you have all of your orbitals filled with electrons, all the electrons are paired up, that's called diamagnetism. Okay, that would mean that your atom or your ion is diamagnetic, and that means that it's not going to be attracted to a magnet. In fact, it's going to be slightly repelled by a magnet. So paramagnetism and diamagnetism, you need to be fully aware of what a paramagnetic substance is and a diamagnetic substance is. All right, let's try another practice. What is the maximum number of electrons that can be present in a principal quantum number for which n is equal to 3? If n is equal to 3, what are my possible values of L? I could have 0, 1, and 2. Well, if my L is equal to 0, my possible values of ML are 0. If my L is equal to 1, my possible values of ML are -1, 0, and +1. If my L is equal to 2, my possible values of ML are -2, -1, 0, +1, and +2. What's the total number of orbitals? Who could tell me how many total orbitals I have for an n equal to 3? Not a trick question. Absolutely. Perfect. Trevor, it's 9, right? I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? I have a total of 9 total orbitals. Okay. It's asking me about the maximum number of electrons. I can hold 2 electrons in each orbital, can't I? Okay. If I have 9 total orbitals times 2 electrons, that gives me a total of 18 total electrons. That's the maximum number of electrons I could have in the principal quantum number, in the principal level for which n is equal to 3. 18. That's the number. Try another one. An oxygen atom has 8 electrons total. Write the 4 quantum numbers for each of the 8 electrons in the ground state. Well, if I have a total of 8 electrons, okay, oxygen, come on, oxygen has 8 electrons. Let's write out the electron configuration. Right, I'd have 1s2, 2s2, and 2p1. Who could help me out? How many electrons would I have in a p orbital? Exactly. I'd have 4. Right? And if you're confused, if you're like, well, where did you get that from? Look, oxygen is found right here in the periodic table. If you divide this in half, the oxygen is right here. So you have nitrogen, carbon, come on, carbon and boron. Okay, you have hydrogen, helium, lithium, beryllium. So look, it's a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. The electron configuration for oxygen is going to be 1s1, 1s2. Let's keep going. 2s1, 2s2. 2p, 1, 2, 3, 4, 2p, 4. So that's my electron configuration. Why did I know always to stop at 2 for my s's? Because there's only one type of s orbital, and each orbital can hold a maximum of 2 electrons. For p, why did I know that I could go up to 4? Because for p, I can hold, p has a total of 3 orbitals. Each one can hold 2 electrons. That means I can go up to 2p6, right? So there's my electron configuration for oxygen. Let's copy it. We'll bring it back wherever we were, right down here. Oops. No, oops, didn't mean to do that. There. So there's our electron configuration for our oxygen. Now, what does that mean? Let's start with these 2 electrons right here. For the 1s, my n is equal to, remember we're listing n, l, ml, ml, and ms. Okay, let's start with the 1s2. So my n is going to be 1, my l is going to be 0, my ml is going to be 0, and the first electron is going to be plus a half, and the second one will be minus a half. There, I've taken care of the 1s2 electrons. Move those down here. Now let's do the 2s electrons. Right? Principal quantum number 2. Since they're s, my L is equal to 0. My ML is going to be equal to 0. First one will be plus a half. Second one will be minus a half. There's half. We're halfway through the problem. Okay? So there's my s electron. Okay? I'm going to do the p a little bit slower. There's 3 types of p orbitals, aren't there? Px, py, pz. I'm going to have 1, 2, 3, according to Hund's rule, I want the maximum number of parallel spins. 1, 2, 3, 4. Okay, so I'm going to have n is equal to 2. Okay, my L is going to be equal to 1. I'm doing this one right here. If I call this -1, 0, and +1, I'm going to have -1, and it's going to have a plus a half. Okay, I'm going to move that one carefully. Copy it. Okay. Oops, not, dang it. All right, I'm going to try not to swear. Try again. Copy. There we go. Okay, so there's the first one. Delete this circle. Do the next one. This one here. It's got n is equal to 2. L is equal to 1. ML is 0. And it's pointing up, so it's plus a half. Okay. There's the next one. I've got 2 more left. I've covered 6 already, and there's a total of 8 electrons. We'll keep going. Let's do this one here. It's got an n is equal to 2, and L is equal to 1. My ML is plus 1, and it's pointing up, so we're going to say it's plus a half. There's the 5th one. Sorry, the 7th one. Okay, and then I have one more. I'm kind of running out of space here, aren't I? Try and move these down here, maybe like that. And we'll do the very last one. I'll give you a second to see if you can come up with the set of 4 quantum numbers. Oops, for this guy right here. This one is pointing down. See if you can come up with those. If you have the time to type it in, give it a shot. All right. I see Sierra and Trevor have got an answer. Let's see what they got. See if they're right. Okay, it's going to be 2. It's a P. It's in the first orbital, so it's -1, and it's going to be minus a half. You're both 100% correct. Perfect. We'll put that down there. Oh, son of a gun. Come on, Apple Pencil. Come on. Maybe it's dying. I don't know. There we go. We did it. So we literally came up with a set of 4 quantum numbers for every stinking one of these 1, 2, 3, 4, 5, 6, 7, 8 electrons. Again, you can do that for any atom on the periodic table. Give me a thumbs up if you think you can do it. Now that you've seen it done a little bit and gave it a little bit of a try. All right, awesome. That's awesome. Here are the electron configurations for all of the elements in the periodic table. And as long as you have a periodic table and you can fill in, 1, 2, 3, 4, 5, 6, 7, SPDF, and you know that for the D's, you dip down by 1, for the F's, you dip down by 2, you can write the electron configuration for anything. Let me just show you one more trick, okay? If I wanted to write the electron configuration for chlorine, okay? So again, I don't have a great periodic table here, but it's not divided up vertically, but I'll try my best. So chlorine is found right here. Chlorine is element number 17, okay? So chlorine has 17 electrons like that. So we'll kind of divide it up. This 1, 2, 3, 4, 5. Yeah, that's good. Okay. So if I was to write out the electron configuration for chlorine, it's 1s2, 2s2. Now I've used up 4 electrons. That means I've got 13 to go. 2p6. Now I've used up 10. That means I've got 7 to go. Then I go 3s2. I've used up 12. Then into my 3p, I've got 3p1, 3p2, 3p3, 3p4, 3p5. 3p5. Done. That's my electron configuration for chlorine. If we back up here, it's going to be really hard to see. If you look at chlorine, you see how it says right here. It doesn't say what we had written down. It says neon in square brackets 3s2, 3p5. That's called a shorthand electron configuration. And in fact, you see all of these elements at the beginning of all these electron configurations. You notice that what they have in common? They're all noble gases. Well, let me show you how to do that. If I look at chlorine, what is the noble gas that comes before chlorine? Not the closest noble gas. The closest noble gas to chlorine is, in fact, argon. It's right here. But the noble gas that precedes or comes before chlorine is neon. Okay? So if you want to write a shorthand, the way that you do it is you write down the noble gas that precedes the element in square brackets. What's the electron configuration of neon? It's 1s2, 2s2, 2p6. So that covers all of this part right here. So then you just write neon 3s2, 3p5. That's called shorthand electron configuration, and obviously based off of this slide, it's very popular. It's very common. If you're wondering, do I have to know how to do both? The answer is, of course. All right, well, with that in mind, let's try a couple here. The electron configuration for sulfur. Okay, sulfur has a total of 16 electrons. We'll start at 1s2, 2s2, 2p6, 3s2, 3p4, like that. Look, 1, 2, 3, 4, 4 plus 6 is 10, 12, 12 plus 4 is a total of 16. There's my electron configuration for sulfur. Let's try another one that's kind of interesting, and it's palladium. But they're telling you something interesting. They're telling you that it's diamagnetic. Okay? What does diamagnetic mean? All electrons are paired. Okay? You have no unpaired electrons, and therefore it's going to slightly repel a magnetic field. Now, if you go on your periodic table and you try to find palladium, you'll see that it's element number 46. Okay? So palladium has 46 electrons. I'm going to do it a little bit quicker just because we're running out of time here. I'm already going over time. But the noble gas that precedes palladium is krypton. Okay? And krypton has a total of 36 electrons. So krypton has 36 electrons. Palladium has 46. 46 minus 36 electrons equals 10 electrons. So we've got 10 electrons to account for. What comes after krypton? After krypton, you're down into a 4s2. And then if you count over in your palladium, you go 1, 2, 3, 4, 5, 6, 7, 8. So it would be 3d8. There's a problem with this, though. There's one type of s orbital, right? It's got 2 electrons in it. So here's my s orbital. For my d orbitals, how many types of d orbitals are there? There's 5. 1, 2, 3, 4, 5, and there's a total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, these are my d orbitals. So this is my 4s and this is my 3d. There's a big problem here, isn't there? Because we've got 2 unpaired electrons. That would mean it's paramagnetic. And so what happens if palladium is diamagnetic? That means that these 2 electrons that are in the 4s, they actually get put in the 3d orbitals. So instead of this being the electron configuration, the correct electron configuration is krypton in brackets followed by 3d10. Those 2 electrons that were in the 4s orbital, they move into the 3d orbital so that your 4s orbital is empty, but your 3d orbital, 1, 2, 3, 4, 5, has all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and therefore they're all paired up, and the atom would be diamagnetic, meaning again, all electrons are paired, and it is not attracted to a magnetic field, rather it repels a magnetic field slightly.